some things that we're able to do in sort of modeling physical reality. Right. I mean, having a notion of space and time is what allows like Newtonian mechanics to take place. So I'm interested in sort of trying to bring this into the like modeling physics world.
Mm-hmm.
And I'm still kind of stuck a bit in how we're actually modeling space and sort of wrapping that around to an understanding of physical reality. And I'm also a bit confused just in terms of the new calculus that you presented, that there seems to be some sort of maybe expressivity or modularity that's lost from the row calculus, in that normally when we have the statement, for y from x, drop x, or drop y, what we're expecting is that's like a little process atom that whenever it's put into context with something sent and possibly a whole bunch of other things, that the Q that is sent on channel X is going to be run sort of in the context that would be created if you had sort of removed the input guarded section of that process and replaced that with a whole. But we don't necessarily have that sort of like self-referential capability in the new production rules, at least from what I'm seeing. You sort of have to, in order to do something like that, you would have to construct a process with that input guarded process as a part of it. And then you would have to construct a context, which would be sort of everything that's running in your context with a hole where the input guarded process was. So that's where I'm at.
Okay, good. So this is more a set of questions about the design of that particular calculus, as opposed to the design of a calculus for yourself.
There were two kind of comments / questions in there.
Yeah, sure, and that's totally reasonable. Good. So we can kind of go depth first, or we can go breadth first. I can respond to you, or we could. How about I respond a little bit, and then respond, and then we can move on and get others' thoughts. So with respect to the row calculus in space, the notion of space here is literally a position in a data structure. You could think of every term structure as effectively a tree structure. Does that make sense?
Yeah.
Okay, great. So then the zippers that we generate for a term structure are going to give you notions of location in a tree, but we're only going to admit special kinds of trees. And so you can think of it as a specialization of a tree. And so now that's your general notion of space. You just get to live inside trees. And so in this sense, it's very, very similar to the ambient calculus. Right? The ambients form a tree. There's a kind of nesting of ambients. And then processes can go in and out of them. Here we have a similar set of primitives, right? So you can go in and out of them. Now the difference, as you pointed out, is that we kind of have this trifold sort of thing in the sense that it's not split across two things, right? So that I'm talking about is the dynamics. The dynamics in the calculus is not split across, a pair of things. It's split across three things. So the biological models are helpful here, at least for me. We're not allowing. What we're saying is we're modeling phenomena where reaction happens. Only catalyzed reaction happens, is I guess the way to put it. And so that's why you need this third COM agent. So in some sense, it's not as modular, but in another sense, it's more modular, right? It's just that you've factored out location information. And if you want to design things, which is what I showed with the last example in the calculation, if you want to design things, you have to be aware of the execution context, right? So when you factor your computations, you have to factor them in terms of these execution contexts. Does that make sense? Does that help at all?
Yeah, it does. I guess, well, actually, no, I mean, it does make sense, but I don't think that really changed my understanding much. I guess it's, when I look at the example, of the miniature process that's like an input guarded process that's running whatever it got back. I guess, yeah, maybe what's confusing me is that the catalyst and the like location are sort of packaged up together in this.
That's right. That's right. Catalyst and location, and that's sort of by design, right? What we're saying is that things operate differently in different contexts.
Mm-hmm. But then, yeah. Okay.
So, and we see this in human social behavior, right? One of the places where I was most struck by this as a parent is the difference between my child's behavior at home and my child's behavior at a sleepover. So what I realized is that there are at least two faces to the child. At home, the child often has resistance to authority. Right? They're catalyzed in some sense to express their own will. Not your will, but mine. No, I don't want to go to bed. No, I don't want to eat my vegetables. Whatever it is. Whereas when they're away, the biggest thing is that they're sort of, they end up being on their best behavior, and a lot of that has to do with their perceived level of safety. At home, they're very safe, or at least hopefully they feel safe. And whereas away, they're not quite as safe or not quite as certain about their safety. And as a result, they're going to engage in social behavior that's more that's likely to create safety, shall we say? And so they present whatever they've learned at home with respect to what they consider to be best behavior.
Sure.
Yeah, exactly. So it's a natural split. And I remember as I was beginning to recognize this and observe this, the parents of my child's friend would describe their behavior. Oh, so and so is like such a great guy. He, so attentive, so listening. I'm like, wait, are we talking about the same child? Sorry about the noise here. Anyway, the point is that different things behave differently in different contexts, and here the context is also the notion of location. I don't know. Did that help?
Yeah, I think so. I could probably keep going, but we could move on if you want as well.
Yeah, sure, absolutely. No, I love this kind of stuff. I'm quite intrigued, quite interested in people's thoughts about the road calculus in space. But I do want to hear, especially if there's anyone who has has a particular problem that they would love to model in a process calculus.
Hey, Greg, I've got a couple things that I've been thinking about recently.
Yes.
So the first thing that, and most of my interests tend to be.
You dropped out, Kenny. Oh, it looks like it dropped completely. Yeah.
Sorry, can you guys hear me now? Sorry, I dropped
Shoot.
out.
Yeah, we can hear you.
Okay, good. Sorry about that.
Maybe we'll come back.
Grab my laptop and something happened. Okay, so my things that I've been thinking about a bit social. So the first thing is the notion or expression of a group of things being greater than the sum of their parts, whereas it seems intuitive from a description of something, but not from a I guess from an actual description that you could model. My intuition here is that the thing being talked about that's greater is somehow transcendent or different than the thing being summed. But I'm not exactly sure what the relationships are going to be, but it is an interesting property, because if you can test for this, where you have some property or some behavior of some phenomena of a group of actors or individuals or people, like intelligence, for example, where they all have some quality, but together in some process, it's collectively greater than any one of us, or either the sum of all the parts or any one of the parts. That's one thing I have a lot of interest in. Another thing that I see around me a lot is you might consider this something like inequality, or the 80-20 rule, or the Pareto distribution, where things in nature, things in social structures tend to start to condense into certain patterns of certain ratio, or at least closely related ratios. And it seems to be such a prevalent thing all around that there's probably some sort of description of more than just the processes of spreading things out and getting them into certain concentrations. So those are the two things that I'm interested in, and one that I'm not exactly sure about how to go about creating a process calculus for it is whether taking observations of these principle or these phenomena from the top and working your way down is the best approach, or something different if there's some base principle to start with and try to work your way up, or some combination of in between.
Understood. Yeah, both of those are sort of intriguing and fascinating phenomena, aren't they?
Yeah.
With respect to the first one, we can easily craft examples. And as you were speaking, the first example that popped into my mind was the row version of the Y Combinator. Does anybody know or remember the row version of the Y Combinator from the original paper on the row calculus? Do people know what the Y Combinator is? Okay, I'm kind of guessing that from the silence that the Y Combinator idea is a fresh idea. Is that the case? Anyone been exposed to the Y Combinator?
This is Kayla. I have been. Basically, Y Combinator is kind of like the sweet spot where it's a paragraph that f of x is equal x, where basically regardless of the input that you give, you get that output back.
The Y Combinator is an encoding in a term in the lambda calculus to find a fixed point. So it's the basis of recursion. The y so y of f of x is going to, so y of f of x is going to be um, f of x, right? So it finds the fixed point. The process doesn't move, or is going to be x, right? Sorry. So the it's the thing where you apply a fixed point. F of x is has got to be, it's got to be unmoved, right? So this is the when you think about it in terms of recursion, the meaning of a recursive function is often given in terms of the unfolded calculation, and so the unfolded calculation is really the fixed point of your recursive function. So I've kind of not given the most articulate verbal thing because I'm a little distracted getting into the house, but it's suffice it to say that the y calculus is what allows you to find to within the calculus define recursion. So when I first encountered, or not when I first encountered the y combinator, but when I first encountered the process calculi, I said, what will be the concurrent equivalent of the y combinator? And that, of course, immediately says that you have to have a higher order calculus. You have to be able to encode processes as terms that you can move around. So that gives an interesting desideratum right away. But if you look at the process that receives y and then drops y and then forwards, so let's say it receives y on x and it drops y in parallel with forwarding y on x, right? So basically all it is a little harness to run something and then forward something. And now if you take that process and put it in par with another process, and you send that on x to you, this little test harness process, what happens? Well, you drop the par of your process p together with the process that on x waits for y and then drops y and sends y on x, and you're running that in pair. So remember, that's the thing that we sent on x, right? And then you're running that in parallel with the test harness again. So what this will do is it will make an infinite number of copies of your process P running in parallel. So this is replication. Now, does everyone see the equation? Should I write it down? Can someone else write it down? Just checking in. Can you hear me?
Yes.
Okay. Does someone want to take a shot at writing this down? There's no recursion in the equational definition, and yet it ends up giving you the definition of the pi calculus bang. Does that make sense? How about I I write it down for people. It seems like we don't have a good understanding here. So let's.
Yeah, I mean, I've seen it and understood it in the road calculus paper. I'm not confident that where I'm at this morning, I could write it down from memory.
Oh, okay. All right. Yeah. No worries. No worries. Let me go ahead and plug in my machine, and we'll take that on, and then and the reason I mention this, Kenny, is because you can take this behavior and chop it up into its component parts, and as a result, without any one of the components, you will not get the full behavior. You won't get recursion. You need the ensemble in order to get the recursion. And so you literally get a sum that is greater than its parts. A similar kind of thing, and in many ways, the result, the idea that we're exploring here is even more profoundly explored in Yoshida's papers on minimality and separation. So Yoshida's papers about providing a combinator like structure for the asynchronous pi calculus. What she shows is that there are about 7 processes that when you have this ensemble of 7 processes, you can model, you can internalize the whole of the asynchronous calculus, right? So you just have these little tiny process-like structure or process structures, and when you have all 7, you recover the pi calculus. If you don't have any one of them, then you have a subcalculus of the pi calculus, and she gives a characterization of that subcalculus. So that turns out to be another clear example of what you're talking about, where the whole is greater than the sum of its parts. Does that make sense? Does that?
Yeah, that's interesting. That the way that works is that there are these. So you can have descriptions of processes in general, or processes specific, meaning that do certain things or have certain characteristics, and then combining them in certain formal ways can create more generality or less, and they all seem to be sort of connected. But like you're saying, at some point you need higher level descriptions if different behavior is desired. But it seems like at this point with a mobile process, we're close to being able to at least peer into some of these things at least a particular level that's more nuanced than what we've been able to do before.
Right, but the reason I mentioned the Yoshida one is that in her version, she's just got the ordinary pi calculus. Doesn't have to be higher order. The Y Combinator thing forces higher order, but the general idea of combinators gives rise to this greater than the sum of its parts kind of thing.
Yeah, got it. Yeah.
Yeah, exactly. So if you want to explore the greater than the sum of its parts kind of thing, then the first place to look is in combinator style presentations. Because each of the combinators gives you a kind of characteristic behavior, right? So for example, in Yoshida's combinators, you have the nihilist character, right? That nihilist character just takes something in on a particular channel and throws it away. That's all it does. It's always getting rid of stuff. It's the garbage collector. And at the other end of the spectrum, you have the duplicator behavior. So it takes whatever you give it and it spreads it out onto 2 different channels. So that's That's another sort of characteristic behavior. And then you have branching behavior where it'll send it on the left channel or the right channel, something like that. It's a little bit more subtle than that in Yoshida's version. But the important thing is that each of the combinators represents a kind of scheme for or archetypal behavior is one way to put it. You have these processes that are sort of like characters. And when you have all of the characters around the table, then you have a good murder mystery. But if you don't have all the characters around the table, then the story gets boring. That's one way to think about it. So hopefully that makes a certain amount of sense. Now, with respect to your other one, I'm going to come at it obliquely. Are you familiar with, in biology, we often have these kinds of power laws?
Yeah, absolutely.
Yeah, so with computational calculi, it's very natural to imagine that you get power laws. And the reason is because you have these recursive definitions of the term languages. And then the computational part of the term languages uses the recursive structure of the terms to run the computations. So it's extremely natural to find power laws in computational calculi. And I think I'll just leave it there because I would love for other people to go and pick up this idea and see if they can sort of find sort of some natural power laws in various computational calculi. I think it would be it's a very natural and easy idea to go after, and I'd love to be surprised. I'd love to have someone who takes it on and finds it and finds some interesting results there. So that's a very good that's an intriguing area of research. With that, we're sort of halfway through, and I want to switch gears, and I want to switch gears to an area that I've been hoping to cover. So if people remember, when we talked about bisimulation, I kind of hinted at an idea of formulae, but I didn't really say where the formulae came from. And so now I'm going to talk about how to generate those formulae. That the formulae are in fact not mysterious at all, that there's an algorithmic way to generate the formulae. So in particular, Robin Milner and Jamie Leifer and Peter Sewell came up with an algorithmic way to generate bisimulation from a set of rewrite rules, and nice bisimulations that were congruences. And what I'm going to do is I'm going to go the other direction, right? So remember what we had was this here. Let me just do a screen share. So what we had was this characterization here, right in the middle of the page, that bisimulation corresponded to a kind of testing or probing, a high-level testing or probing. So two processes are bisimilar if and only if, for any formula which we think of as characterizing a test of a process, for any formula, P satisfies the formula if and only if Q satisfies the formula, right? So you can't devise a test which would distinguish them. or you can't cook up a formula which says something that P responds to in a way that's different than the way Q responds to it. Right. So that's the key idea, that these two notions are exactly the same. And so if we could algorithmically generate by simulation, it stands to reason that we ought to therefore be able to algorithmically generate the formulae. Does that make sense?
Yes.
Yeah.
Mm-hmm.
Cool. All right. So I'm going to show you how this is done, and this is the beginning of ladle. And I'm going to do it first for a term language that doesn't have a reduction relation. So it's only got the term formation rules, the constructors, and the structural equivalence. And even there, because we're operating at such a powerful level of abstraction, we get lots and lots of cool stuff. Now, as preparation for this, what I'm going to do is I'm going to break down the sort of meaning of formulae in a funny way. So notice that we have this idea of a process satisfying a formula. And that means that we could consider collections of the form all the processes P that satisfy the formula phi, right? So if we were going to collect them in a set, right, then here, that would look like. I'm going to get rid of this stuff here. And then grab this. And we can talk about the extension of P, which I will write this way. I think I might have it here. Yeah, here we go. And then okay, so the extension of phi is going to be equal to all the P such that P satisfies phi. Now, if I were that's if I were doing it in sets. So what that just to make it clear that we're talking about sets, I'll put set as a subscript so that we're clear that that's what's going on. Okay. And so just checking in, everyone's comfortable with this notation?
Yep.
So if you think about the processes as coming from a particular data source, so in this case, the data source is L of M. So remember, I had adopted this notation L of M, where M is the grammar that generates the set of all terms. So we could think of how do I say this? Well, in general, what we're going to find is that the semantics of formulae are going to be given in terms of a notion of collection and a and all the terms that bear witness to that formula. That's the basic idea. So the semantics of a formula are exactly those programs that exhibit the property of the formula. This is the general shape of our logical semantics now. And we don't have to just collect things as sets. Here, drawing from this particular data source here, we're going to collect the ones that satisfy the formula in whatever notion of collection we have. So if it's set, if I come up with the same term a second time, then I'll erase the fact that I got it a second time, right? They'll be collapsed and they'll be identified because A union A is equal to A. And this is a basic property of sets. But if I have lists, A append A is not the same. And so if I were collecting it as lists, then if I hit P a second time from whatever my data source is, then I would include it twice. If I were using trees, then I would end up locating these terms. So if I use tree instead of set, I would end up locating these terms somewhere inside a tree, right? So their location would also matter. Sets kind of erases location, but as we drop those kinds of constraints, then we get more and more information about how we traverse the data structure, generating terms, and then checking the properties of those terms. So all of that is a setup in the following way. We've already agreed at the outset of these talks that a term language corresponds to a monad. So the Levere theory for the term language is going to correspond to a monad. So that's why I use the letter M here, because it's a monad. And now it turns out that our notion of collection is also going to be a monad. And what I've just said is that the meaning of formulae is going to be the application of the collection monad to the term monad. And what the ladle algorithm says, so let me just write that down, right? Just so that we get kind of a clear picture of this. So I'm gonna put my collection monad as C, and just as a mnemonic device, I'm going to change that from an M to a T so we know it's the term monad. Okay. All right. So then the meaning of formulae is going to be given in terms of sorry, just wanna, C of T. Now it's really a way of combining monads. It's a little richer than just composition, but we can talk about those subtleties in a minute. Right? So now all I have to tell you is what the formula are. How do we get the formulae in the first place? And what it will turn out is that we generate our formulae by knocking holes in terms. So we generate them recursively, and we knock holes in terms, and we know how to do that, right? We take the derivative of the term, and then we knock a hole in it. And then how do we fill that? Well, we fill that with collections. Collections of terms recursively. So what we're really saying is that phi itself, is given in terms of T of C. So then our semantics is going to be of the type, so this function here for some input is going to be T of C to C of T. That's what the semantics of formulae essentially does. I'm kind of giving it in a slogan form. There's a lot of subtlety here that I'm erasing, or skipping over. But I just want you to get the feel for it, the flavor of it, right? So that's what we're saying is that the logic, the meaning of logical formulae, these kinds of things here, is given in terms of a distributive law that takes terms built over collections to collections built over terms. So in order to keep this more grounded, because it's very powerful when stated in the abstract, when we keep this more grounded, we can see a little bit of the power of it, even at the lowest possible level. So we're by now very, very familiar with monoids. So let me now present the grammar, the Levere theory for a monoid. Okay, so we're going to say that M and N range over, a monoid has an identity, right? And this is monoids coming from some generator set G. So I have G sub I, and we also have M star N here. So the GI is, I'm just doing it for a finitely generated monoid. Okay, and now what do we need in order to complete this? Well, we need our usual suspects. The M star E is equal to, and I'll use triple equal so that we're clear that this is a structural equivalence. Is equal to M, which is triple equal to E star M. And then we also have M1 star M2 star M3. Okay, this should all be, like bread and butter now. Is this all making sense? No confusion here?
Yep.
Okay, awesome. almost done with my OCD discharging of neatening up the subscripts. Last one. Okay. All right, so there we go. So that's our Levere theory for our monoid. So now that's our term language, T. That's the T, the monad T. And now for our collection monad, I'll use set because it's most familiar to folks in coming from this culture, this time. But now I'm going to give the semantics of the formulae and the formulae all at the same time. So I'm going to say the meaning of true is going to be equal to L of M. Okay, so there's no constraint on true. True denotes the entire set of monoid expressions. Okay, and you're going to ask me, well, where does true come from? And I'll explain that in just a minute. And we're going to say that the negation of a formula phi. So now I better do this like this. Is equal to L of M, take away the meaning of the formula phi. And then here, it's going to be the meaning of phi and. So I guess I'll use that for and. C is going to be equal to the meaning of phi intersect with okay, so all of this chunk here actually comes from the set monad itself. Here, we're just generating these things out of operations on the set monad that are all present in the set monad. So this has nothing to do with the terms and just with the collection monad. So one way to think about it is, remember how we talked about how formulae are going to be terms with holes knocked in them. So you can talk about the context that is just the whole, no extra term structure. And then all of the sets that you might get from the set, from the collection monad, could be placed into the whole context. So here's this one. That's the most obvious set. So if you place that in the term context, which is just the whole and nothing else, then you get true. And then the remainder of this derives from the set structure itself. So each one of these is taking different set structure and placing it into the unconstrained context, the context that is just a whole. But now we can go a little bit further. We can, so if this is the set part, we can now also use the term part. So we're going to get a logical formula E, and I guess what I'll do is I will make it italic so you can see that it's different from this E. And now this is going to be the set of all little m's that live in L of m such that m is triple equal to, I can get it from here. So in terms of monoid expressions, that's going to be E, E star E, E star, E star E, etc. Right? So that's what this set is equal to. Likewise, for each GI, we're going to have a very similar kind of notation. Or similar kind of semantics. So each generator also provides a logical formula, which, so this is going to be GI, GI star E, GI star E star E, etc. So that's the set of monoid expressions that are all equivalent to the generator GI. And now we get something fresh and new, which is the term constructor gives us a new kind of formula constructor. And this is going to be the set of all, actually, let me do it this way. The set of all m such that m is triple equal to m1, oops, m1 star m2, where m1 there we go. Okay, let me give it a little bit more space, where m1 comes from the meaning of phi, and m2 comes from the meaning of c. And then we need element of. Okay, are people following this basic construction? So basically it says it's all the m's that decompose into two things, the first of which comes from phi and the second of which comes from c. So it sort of picks out that the m has composite structure. And that's it. There's no reduction relation. So we end up with that's basically our entire formula language. But that formula language already turns out to be incredibly powerful. So, for example, I'm now going to give you a new kind of formula, and that formula is a one-liner for primality. So I'm going to pick out exactly the primes for this monoid. Now remember that the natural numbers under multiplication form a monoid. So when I talk about primality, I literally mean primes like the prime numbers that we grew up knowing about in grade school arithmetic. But it also picks out primes for a wide range of other monoids, and I will talk about some of those in just a second. So first, let me just deliver on my promise, as we're almost out of time. All right, so the promise is primality. So I'm going to give you a one-liner for primality. How about get rid of those? Okay, and that's going to be, well, what do we know about primes? Primes are not allowed to be the identity. So can we express the idea that it's not the identity? Yes, indeed we can. We can say it's not E. And then, but we also have some other constraints, like we can't decompose it into a multiplication of things which are not trivial, not the identity. So we could say it's also not decomposed into a multiplication of things which are not the identity. There, one-liner for primality. Now you can check for yourself just using the definitions I've given here that in fact this picks out the set of generators GI, which is exactly what we'd expect to be, the primes to be. Now, let me stop there because it's 7 and just check in quickly. Does this make sense? I'm gonna rearrange this a little bit.
Yeah, I understand everything that's on the page here. I'm having trouble tying it back to the collection of the terms versus terms of the collection.
Right, and that's like literally right in front of us here.
Right.
So here, each one of these is a piece of term structure that we've knocked a hole in. In this case, with the constants, more or less, the data that is supplied to generate the term structure, we don't knock a hole in those. But here, it's clear that we've knocked a hole, right? In fact, we've knocked 2 holes. We've knocked a hole on the left of a multiplication. We've knocked a hole on the right of the multiplication. Right? And then we're saying, yep, however you can fill those holes that respect this constraint and this constraint. That's what's going on. And here, we're just, we get it from the set structure. It's the collection structure that's giving us this formula structure here. But now let me leave you with a basic notion, a basic idea, which is what's one prime, or what's one monoid that we can think about? Well, here's a monoid that we know and love, and that is that processes together with parallel composition together with the 0 forms a monoid, right? So parallel composition is our star, 0 is our identity, and P is, the set of, or denotes the terms, ranges over the terms. So that's a monoid. Now, what does the notion of prime, this notion of prime that we've written in a single line formula, mean for that monoid? It means that we pick out exactly the single threaded processes. Now, I think that's pretty darn cool. So we've given a general characterization of primality, and what we've done with the ladle algorithm is to interpret it in terms of the monoid of concurrency, and lo and behold, primality is exactly the single-threaded processes. That's just astounding to me. We didn't, like, the whole thing was algorithmically generated. We generated these formulae entirely as an algorithm. Then we used one of the new formulae constructors in order to, sorry, this should be a star, not an and. There, it may have been confusing people. All right, so you're not allowed to compose them as opposed to and them. And then we use this to we use the new constructor to write down a formula that is much harder to express in sort of a traditional logic. And then we gave that interpretation across a range of phenomena, from multiplication and factorization in ordinary multiplication to parallel composition. So we have a unified single-threadedness with primality. That gives you a sense of the power of what we're doing here.
Thanks,
All right.
Greg.
Yeah, thank you. It's time for Casper. Thanks. See you guys next week. I think, is next week the last one, or is there one more?
We wanted 12 of them. So is that right, Greg?
Yeah, I guess 12. That's right.
I believe, let me see.
Is next week 9 or 10?
No, this week is 9. So next week